All right, an educative day can keep unemployment away. And then I finally got the second part of the rhyme. So an educative day keeps unemployment, can keep unemployment away, but a video about it might make you a hit in general. So, two heaps introduction. We are on our what now? What pattern is this? I think our sixth pattern. Yay, we've come a long way. And so we're going to be looking at how you can use two heaps to solve uh, interview questions for software engineering. So typically you're using two heaps. Some things to note about using a heap: it takes O of log of n to insert an element into a heap, O of 1 to access it, right? The root element of the heap. And so there are two different kinds of heaps. We have the minimum heap and the maximum heap. So minimum heap keeps the smallest value at the root, while the maximum keeps the largest value at the root. And in some problems, you find these things useful, these facts useful. They help you speed up quite a few things. So we'll construct a minimum heap from the array below. It might help us visualize it. So it's going to look like this. And it's going to step through it. It's a minimum heap, so the smallest value should be at the root of the heap. So the smallest value is always at the root. 2 smaller than 3, so it displaces it. We can take it again from the top. So we're evaluating 10, we add it to the list. Since 10 is less than 11, 11 becomes its child. 3 is smaller than 10, so they're swapped, right? It displaces it and it's swapped here. 7 is smaller than 11, so it moves 11 down. And then 2 is smaller than 3, and it displaces 2. So that the smallest thing is always on top. That's the shtick about the minimum heap. And now we're doing an introduction video, so it might be slightly longer, but I'll try and get everything done in 10 minutes. So maximum heap, this time the biggest thing is on top. So we have 10, 11 is now on top, and it stays on top because it's the biggest thing in the array. And that's all. It's a minimum heap, it's a maximum heap. You can read more about it because there are quite a few details. I even pulled up some stuff I learned about it in ChatGPT. For instance, we typically store heaps as arrays because arrays have like O of 1 indexing, like when you want to pluck something from an array, instead of how we store linked lists with data and pointers to the next thing. So it saves you quite a bit of time when you just save it as an array under the hood. It's pretty cool. So these are examples of problems you can solve, and we'll be solving these, at least one of these. Find the median of all windows of length k in an array. This is a very interesting problem, but it's not for today, it's for tomorrow, the problem for tomorrow. But we'll go into more detail of it tomorrow, not today. This problem, though, we're going to cover today in the next few minutes. And it's the maximum remaining capital from selecting at most k projects. And I'll break it down shortly. I mean, you can read this if you want, but I feel like the explanation will do a better job at explaining things. So if you need to repeatedly calculate 2 maxima, 2 minima, or 1 maximum and 1 minimum, then you need this problem. If you don't need to track 2 extreme values, that is minimum or maximum values, but only 1, you probably don't need 2 heaps. You don't need to repeatedly calculate the extreme values, but only need to calculate it a fixed number of times, then you don't need 2 heaps. If the data is already sorted, then there's no benefit to using heaps. So here are some real world problems. During a user session, there's a possibility that packet drops and buffering might occur. You want to record the median number of buffering events that might occur in a particular session, which could then be used to improve the user experience. Okay. And Netflix, for example, might want to know the median age of their viewers. So you want to update that efficiently whenever a new user signs up. Pretty cool. These are some problems that need to be solved with two heaps versus other patterns. Sort the characters by frequency. I'll say it's another pattern. Median of subarray of size 3. Median. Okay, two heaps. The difference between the maximum and minimum of elements in each window. As a size 3 array. I might just give it two heaps. Even the string find another substring of 5 distinct characters. Nah, this was like a sliding window problem. Submit. Am I sure? Yeah. Yeah, I got it. And we can look through explanations by expanding this, although it makes the UI a bit clunky. Not super important to keep track of, but I mean, worth seeing. Let's look at the maximized capital problem. So, you can read all this large body of text, but the reality is you want to, let's just look at an example. So we have K. An investor can pick K things to invest in, and he has his initial capital of 1 of C. And we're also given like an array of capitals and the profits. So this is a business. The first thing here represents a business that he can invest in. The first thing here represents a business he can invest in and the profit that it corresponds to. So if you invest in this business that requires 1 unit of capital, he gets 2 units of profit out of it. Same thing here. This requires 2, he gets 4. So our job is to maximize the capital based on an initial amount for capital 1. So in this case, he has 1, right? 1 unit of capital. He can invest in this thing. That'll give him 2 units of profit. And then he wants to, as a risk mitigation thing, only invest in two projects. That's what K stands for. Now, the 2 he gained from investing this 1 here adds up, and then he now has 3 to invest, but he has only 1 other project to invest in. So what other project here can he invest in? He's invested in this and he can't do it again. And what you want to do is, okay, he has 3. This requires 3 and gives 8. That's a lot of profit. So to maximize his profit with the capital, he would probably do this next. And that's why you have selected capitals as 1 and 3. Selected profits is 2 and 8. And the maximum capital, including his return capital at the beginning, is 11. And then we return 11. That's what this problem is about. I hope I've managed to make it as clear as possible. Here he can invest in 3 things. He starts off with 2 units of capital. And these are the profits, these are their capital, the business opportunities. So he starts out at 2 and he wants to maximize his profit. So we pick 3. He can invest in 1, right? But 1 only gives 1 profit. But if he does 2, he gets 3 profit. He cannot do 3 in the beginning because he only has 2 to start. So let's do 2 and take this 3 profit, add it to 2, we get 5. Now with 5, what can he do? He has done 2 already. He can do 4, he can do 3, but 4 gives the bigger amount of profit. So take note, he already has 5 units of capital. So he invests in 4. That's the second opportunity he can invest in. He can only invest in 3 total. He gets 7. All right. So then that's 5 plus 7 so far. That's 11. And then he has 1 more slot, 1 more thing to invest in. But then the opportunities have reduced, right? There's only 3 and 1 left. So he's just going to pick 3 and add 5 to that. That's how you get 2, his initial capital, plus his initial profit here. And then this one he picked next. And then the 5 he just mopped up at the end of the day to get 17. And you can see how this can start getting hard to calculate as things get more. And that's why we want to code it up. I hope that makes sense. And we can use this example to see if we've understood. So initial capital of 1, he can do at most 2 opportunities. These are the capitals and their profits. So 1, he can afford only this. It gives him 2. 2 plus 1 becomes 3. He's reinvesting. So 3. He can do 2 or 3, but he can only pick 1 more opportunity because he's already used 1. So it's best to pick 3. And so you have the profit of 5 plus this 2, 7 plus 1, 8. So 8 should be the answer. And voila, we've understood it. We have understood the problem. Now let us walk through the solution. Again, I said this video will be slightly long, but I think we're in the last few minutes of it. This is a problem that uses a heap. Okay, I'm not going to bother with the naive approach because we want to optimize this. And so you can solve it efficiently by using 2 heaps. Minimize the time required to find affordable projects by maintaining the required capitals in a mean heap. So we're going to put all the capitals in the required capitals in the minimum heap, and then find a project with the highest profit to maintain profits in the maximum heap. Okay, so to find the things with the highest profits, you can put profits in the maximum heap. Now we're going to evaluate a maximum of 2 opportunities with an initial capital of 1. And this is how it would look like. We have these capitals, we're going to put them in a minimum heap, right? And we're done. They're all in a minimum heap. And now his initial capital is 1. And we pop the first thing from the minimum heap. And since he can afford to spend to buy 1 thing, we push the profit into a maximum heap. The profit is 2. So now his current capital is 3. We keep track of that as well. And now the next thing is 2. He can afford that. So we push the profit into the maximum heap. But remember, he can only pick 1 other opportunity. Up next, 2, he can afford that. We put the profit in the maximum heap. 3, he can afford it. So we put it in the maximum heap. And so we've populated the maximum heap, we're done. Now we just pick what's the K amount we have left, essentially, from the profits to find what he should invest in. And I hope the code should make it clear. Okay, we can go through the step-by-step solution, but this is where, no, I'm not going to do that right now. Let me just walk through the final solution. A complete solution. So I'll do the thing where we look at this in itself. For example, okay, so this is the solution to the problem. This is the driver code, but this solves the problem. So we have a current capital, starts out as C. The min heap, we initialize to a min heap. The profits, we initialize to a maximum heap. So this is the mean heap. And then we're going to build but first we build the capital. So insert all capital values into the minimum heap. That's what this does. This loop does. So the thing that makes this for us. Yeah. And then calculate the capital of all required number of projects containing the maximum profit. So we're going to loop up K times. And what we're doing is we're checking if while there is something left in the capital heap that we just constructed, check if what is there is less than the current capital we have. So in this case, our current capital is 1, right? Because remember, we started off with a C of 1. So current capital is 1. And we have populated the minimum heap. So 1 is less than or equal to the current capital of 1, right? Here. So we pop it, we take it out, we keep it as a current capital C, and then keep track of its index so that we can take the profit, its corresponding profit, and put it on the maximum heap. So that's what does this, adds it to there. And then it does it more than once. and afterwards 2 comes up here, but then our current capital, this loop terminates because our current capital for now is still 1. So it breaks out of this loop and comes over here. The profit size is it 0? No, it's not. Because that would mean he can't afford anything, right? If it were to break at this point. So instead, what happens is, okay, we know that he can get this profit, so we pop the profit, the thing from the maximum heap, the 2, and we add it to the current capital. We add that to the current capital so that we come again with a current capital of 3 this time, and we can afford what's up here. So we push its profits onto the list because we can afford it, right? And because we can afford it, we're back in this loop where we're pushing to the maximum heap for the profits. Everything we can afford. We can afford this 2. We can afford this 2 as well. And we can afford 3. And so now the size is not greater than 0, right? Because the minimum heap is empty, as you can see. So we break out of this loop, this while loop, finally. And then profit max is equal to 0. That's not true. So this doesn't happen. And we select the project from the heap that contains the maximum profit. So we take the biggest thing from here, right? And we add it to the current capital. And because we have hit K, we've used K opportunities, we just return the current capital and profit. That's it. That's all there is to this problem. Now big O is special. We have a time complexity. So when you push all the capitals in the minimum heap, the insertion is log of n, and you're looping through all the capitals once, so it's n times log of n. But for the profits, you have k. That is the number of selected projects. And so the time complexity is k log of n is, sorry, the time complexity. I was trying to reread this sentence. The time complexity to select the projects with the maximum profits from the heap is k log of n, where k is, you only pick k times, basically. And the extraction process is log of n, so k times log of n. Now, the total time complexity is sum of the 2 time complexities, which turns out to this. And since the upper bound is n, the worst case is k is n. So the worst case complexity will be n plus n, which is 2n. And when you have a constant factor, you can just drop the number. That's why you end up with n log of n. And then we're using 2 heaps to store the capitals, 1 to store profits. In the worst case, we populate the heaps with n elements each. So the space complexity is O of n. Okay. So you need as much space. The space requirements grow linearly in tandem with the number of entries we have. And that's all there is to this problem. Thank you for watching. See you next time.